Today I'd like to talk about yet another way to think about these trig functions. We're going to start off by thinking about a circle with its center at the origin and radius 1, this kind of circle. For the points that are on that circle, x squared plus y squared equals 1. I'm going to think about having an angle with initial side on the positive x-axis as usual, and some terminal side where I've got it drawn in as though it's in the first quadrant. If I know a point on that terminal side, it turns out I'm going to be able to calculate the trig functions as usual, but this point is not a point of this circle. So for such a point as this, x squared plus y squared does not equal 1. Even so, if you start at the origin and go out to this point where x squared plus y squared doesn't equal 1, you do have to cut across the unit circle someplace or the other. I'm going to call the coordinates of that crossing point a comma b. So even though x squared plus y squared isn't 1, a squared plus b squared is, I can think of making a triangle based on the point on the unit circle. I'll have angle theta here. The horizontal distance is the x-coordinate a, vertical is b, and the arithmetic will be particularly simple for this triangle because the hypotenuse is always going to have length 1. The bigger triangle that you could get has x across the bottom, y in the vertical, r along the hypotenuse, but x squared plus y squared is now r squared, as it was before. These two triangles are what are called similar triangles. They both have a right angle in them. They both have angle theta, so the remaining angle has to be the same. In similar triangles, ratios of corresponding sides are equal to each other. So a over 1 and x over r are the same. Also, b over 1 and y over r are the same, and b over a is y over x, which, if you wanted to go ahead and write it in, is tangent of theta. If you cut the middleman out, if you only think about points that are on the unit circle, then a, which is a over 1, is going to be cosine theta, and b over 1, which is b, is going to be sine of theta. So this point is actually equal to cosine of theta sine theta. So I'm not even thinking about that point that's not on the unit circle anymore. I'm just thinking about points where x squared plus y squared is 1. Starting at the usual initial side, construct an angle, and whatever the coordinates of that end point are going to be cosine of theta and sine of theta. You could actually think of doing this. You could get a very long piece of rope and put one end of it into the ground, attach it to a stake, and call the length of the rope 1 unit, and then you could walk around to the thing to draw the circle. Starting at the initial side, you could actually construct some angle that you could measure, and then just think about where you are. The x-coordinate is cosine theta, the y-coordinate is sine of theta. If you remember, a function is a ruler procedure that you feed a number into and a number comes out of. This is a process you could carry out where you tell me the angle, and I'll just look at the x-coordinate of the spot and tell you cosine of theta. If we think about distances on this unit circle, you remember that arc length is radius times theta, assuming that you're measuring the angles in radians instead of degrees. On a unit circle, the r is equal to 1. So if I use radians and if I have the unit circle, the distance along the edge is the same as theta. If I calculate a certain distance along this edge and it comes up, say, 1.5, that would tell me that this angle is 1.5 radians. So in the case of a unit circle using radians as your units of measurement, life becomes very easy. Now, previously, we've talked about ways that you can get values for trigonometric functions at angles other than the one you start with. If I take theta equals pi over 6, we figured out previously that cosine of that is radical 3 over 2, and sine of that is 1/2. If I take this angle and reflect it across the y-axis, I get an angle that is just pi over 6 radians short of being pi radians, which is 180 degrees. So this angle is 5 pi over 6 radians. The coordinates of this spot are the same as the coordinates of the original spot, except the x-coordinate is negative now. So cosine 5 pi over 6 is negative radical 3 over 2. The y-coordinate hasn't changed any. Sine of 5 pi over 6 is 1/2. On the other hand, if I took the original point and reflected it about the origin, which means I have to flip the sign on both the x and y coordinate, the x and y coordinates are the same, except both of them are negative now. The angle that you've got, if you start at the positive x-axis and go pi radians, you will have to go another pi over 6 radians to get where you want to go. Pi plus pi over 6 is 7 pi over 6. So I know that if theta is 7 pi over 6, the cosine value is negative radical 3 over 2, and the sine value is negative 1/2. And there's one other thing that I can do with this original pi over 6 angle. I can think of reflecting it across the x-axis. The x-coordinate's going to remain the same, but the y-coordinate's going to become negative. In this angle, if I started at the initial side and went all around until I get to this location, I am pi over 6 short of a complete circle, which means this angle is 2 pi minus pi over 6. 12 pi over 6 minus pi over 6 is 11 pi over 6. So when my angle is 11 pi over 6, the cosine is going to be radical 3 over 2, and the sine is going to be negative 1/2. If you went another pi over 6, you would land yourself at this spot, and we already know that at that spot cosine is 1 and sine is 0 because the x-coordinate's 1 and the y-coordinate's 0. Now, I'm not actually going to make you suffer through the details, but you could do the same thing using the 45-degree angle, the pi over 4 angle in radians. You could do the same thing with the 60-degree angle, which is pi over 3, the 90-degree angle, and then you would get, for each one of those points, 3 more points to go with them. And what I've done here is I've just indicated the angle in radians, the x-coordinate, and the y-coordinate. The way I got these numbers was exactly the same way we dealt with the pi over 6 in the previous page. So this shouldn't be any great shock. It's just a little bit tedious. But the thing to keep in mind is, for a whole bunch of theta values, I also know the x-coordinate of the spot, which is cosine theta, and I also know the y-coordinate of the spot, which is sine of theta. Now, what I've written down on this page is some of these angle values, some of these theta values. These numbers are the x-coordinates that go with these theta values. So these are the values of cosine theta. These numbers are the y-coordinates of the points. These numbers are going to be sine of theta for each one of these different theta values. This is the first few of them. Here's a whole bunch more of them. And here are the rest of them. The answers that you get out, the sine values and the cosine values, are all either 0 or 1 or -1 or square root of 3 over 2 or negative square root of 3 over 2 or radical 2 over 2 or the negative of that. And radical 3 over 2 is about 0.866. Radical 2 over 2 is about 0.707. So I now have this long list of theta values, cosine theta, and sine of theta to go with it. Now, from that huge list of numbers I've got, I'm only going to write out the theta and the x-coordinates of the points, the cosine theta. So here's a bunch of theta values and their corresponding cosine of theta values. And I want to draw a graph of this thing. On the horizontal, I'm going to put the input into the cosine function. So horizontally, I'm going to have theta. In our calculators and stuff, when we draw graphs, of course, the horizontal is usually called x. And the vertical is going to be cosine values that go with the input values. Not to say too much about it, this is the shape I get. The graph never rises above 1. It never goes below -1. And I've plotted a whole bunch of theta values, starting at theta equals 0 and ending at theta equals 2 pi. And it looks like I've gone through one complete cycle of something. Now, I want to verify this with a calculator, but I don't want to let too much out of the bag just yet, so I'm going to be very careful about something. Getting the calculator ready. So first things first, out of a sense of paranoia, I push my mode button and make sure that I'm in radian mode. If I'm in degree mode, I'll have to fix that up. Secondly, the thing that I'm going to plot is y equal cosine of the horizontal variable is called x in the calculator. In terms of the window settings, we started at horizontal coordinate 0 and ended up at horizontal coordinate 2 pi. About the y range, I already know that y is never going to get bigger than 1 or smaller than -1. So if I allow a little bit of clearance at the top and bottom of the screen, a reasonable choice of settings for the y values would be -2 to +2. So I'm going to push my graph button here. And you see, things are the way we figured they ought to be. This is the picture we figured out by hand. Now, of course, once you've reached 2 pi, you could continue going around counterclockwise. You'll be getting cosine values that you've already seen. So I've got a prediction If I change the range in the x direction from 0 to 2 pi to 0 to 4 pi, I'm going to see more of the same. I now see 2 complete cycles through this graph. A long time ago, we mentioned in passing even and odd functions. If you have the initial side here, and you construct a positive angle theta, and you also construct the negative theta, those 2 points, endpoints, will be different, but they have the same x coordinate. It's the y coordinates that are negatives of each other. So cosine of theta and cosine of negative theta, those are those x coordinates that are equal to each other. Those are the same. The cosine is an even function, and that means that its graph is going to be symmetric about the y-axis. What that tells me is if I alter my window so I've got some negative x's, I'm going to see a mirror image across the y-axis of what you already have. So my current x max is 4 pi. I'll put in negative 4 pi as the minimum and draw the picture. And you see the graph is the way we figure it is. It takes 2 pi units of horizontal change to run through one complete cycle of the graph. And for this reason, we call the period of the cosine 2 pi. Not to make too big a deal of this, you can do exactly the same thing for the sine function, and you get a picture that looks very similar, except now sine of x is going to be 0 when x is a whole number multiple of pi, and instead of sine of negative x being the same as sine of x, they're negatives of each other, which means that this graph is symmetric about the origin. You have high or low spots at odd whole number multiples of pi over 2, like 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, and so on. As a sanity check, I'm going to go in and change y equal cosine x to y equal sine x, and leave my window settings alone. And as you can see, the graph looks like we claimed that it was going to look. The sine function and the cosine function have graphs that are very nice looking. They're very smooth and predictable. They never go out of control. The function values never get real big or real small. There's no breaks in the graph. So it's a very nice couple of functions. The tangent of theta, though, is y divided by x, which, if you want to think about it, is sine of theta divided by cosine theta. We've already seen on the graph of the cosine function, there are places where cosine of theta is 0. That means in terms of the coordinates of the point on the unit circle, the x coordinate is 0. Those places happen at odd multiples of pi over 2. The cosine is going to be 0 at such a place, but still you're on the unit circle. The only way that's going to work out is if y is either 1 or negative 1. So tangent of theta at one of these bad spots would be 1 over 0 or negative 1 over 0, neither one of which acts nicely. So we've already got a prediction. The tangent is going to misbehave. in a sense that the sine and the cosine didn't. To be mercenary, we'll just pull the calculator out and draw the graph. I'm going to draw the graph of y equals tangent of x. We have changed the viewing window previously from negative 4 pi to positive 4 pi. I'll leave it like that for now. It's a little bit hard to see what's going on because of the scaling, so I'm going to reduce the x range. Ordinarily, on the standard viewing window, the x range goes from negative 10 to positive 10. I'm going to change that to negative 5 to positive 5. We can see that the tangent function, like sine and cosine, repeats itself, but it does some other stuff too. Between negative pi over 2 and positive pi over 2, you have this central region, and then in the next chunk after that, you have an exact duplicate of that, and then another one, and another, and it never stops. Backing up, you have exact clones of the piece in the middle, the piece that goes from negative pi over 2 to positive pi over 2. The graph of the tangent function is not nearly as nice as the graph of sine and cosine. We're coming down to the end of our course, and what I want to do to finish is I want to look at a little bit more manipulations of graphs. I want to look at the law of sines and cosines, and I want to look at a few trig identities, and by then we will be out of time. I think we've got just enough time left to cover the material in a reasonable way, so I feel pretty good about the timing. This is all I'm going to talk about today. I'll talk to you in the next discussion.